Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In this session, we are going to solve a general nonlinear programming problem in terms of n variable and with m constraints, where m less than n and all the constraints of inequality type. In particular, we consider a nonlinear programming problem with more than one inequality constraints. We have seen that a nonlinear programming problem with a single inequality constraints can be solved with the help of Hundecker conditions. In this general NLPP with more than 2 constraints also can be solved using the same technique. The first idea is considering a nonlinear programming problem with more than one inequality constraints. Here also we are going to derive the Hundecker condition for a given nonlinear programming problem involving more than one constraints. For that, first consider a general nonlinear programming problem involving more than one constraints. Here constraints of inequality type. So, consider maximum z equal to f of x subject to the constraints g I of x less than or equal to c I. Here I takes the value 1 to m. So, number of constraints is m more than 1 and the decision variable is greater than 0. Here the idea is what we have seen earlier. Now, the introduction of the function h I of x equal to g I of x minus c, the given set of constraints can be rewritten as h I of x less than or equal to 0. So, with this introduction of h, the given nonlinear programming problem with m inequality constraints can be rewritten as maximum z equal to f of x subject to the constraints h I of x less than or equal to 0, x greater than or equal to 0. Here I value varies from 1 to etcetera m. So, by the introduction of the function h I of x, the given nonlinear programming problem can be rewritten in this way. Now, our aim is to convert the m set of inequality constraints into equality constraints. For that, we should introduce some slack variables. Now, by the introduction of slack variable, the given nonlinear programming problem can be modified as follows: optimize z equal to f of x subject to the constraint h I of x plus s I squared equal to 0, I varies from 1 to m. So, in the suppose if we take the first constraints, we introduce the slack variable s1 squared. In the second constraint, we introduce the slack variable s2 squared. So, for set of m constraints, we introduce the slack variable si, so that the given set of inequality constraints become h I of x plus s I squared equal to 0, x greater than 0. Now, this is the problem involving n plus 1 variable in which all the constraints of the form equality. So, the given nonlinear programming problem with inequality constraints is converted into equality constraints. Now, with the help of Lagrangian function, we can easily obtain the necessary condition for this nonlinear programming problem. Now, from this, the corresponding Lagrangian function is L of x s lambda equal to f of x minus summation I equal to 1 to m lambda into h I of x plus s I squared. So, the corresponding Lagrangian function for a nonlinear programming problem with m set of equality constraints is f of x minus summation I equal to 1 to m lambda I into h I of x plus s I square. Now, with the help of this Lagrangian function, we can obtain the necessary condition for the given nonlinear programming problem. The necessary condition is dou L by dou x j equal to dou f by dou x j minus summation I equal to 1 to m lambda I into dou h I x by dou x j equal to 0. The second one is dou L by dou lambda equal to minus of summation I equal to 1 to m h I of x plus s I squared equal to 0. The third necessary condition is dou L by dou s equal to 0 implies that now we have minus 2 s I lambda I equal to 0, where I varies from 1 to m. So, with the help of this Lagrangian function, the necessary condition is dou L by dou x j equal to 0, dou L by dou lambda equal to 0, dou L by dou s equal to 0. So, these three equation gives us the right hand side of equation 1 and 2 and 3. So, with the help of this Lagrangian condition, we obtain the following necessary conditions. We name it as equation 1 and this is 2 and this is 3. Now, from equation 3 we have either lambda I equal to 0 or s I equal to 0, I varies from 1 to m. If we take the case s I equal to 0, then from equation 2 we have h I of x less than or equal to 0. Now, by taking s I equal to 0, from equation 2 we have h I of x less than or equal to 0. Now, from equation 2 and 3 we have lambda I into h I of x equal to 0. So, with the help of equation 2 and 3, for the case s I equal to 0, we get the conditions lambda I into h I of x equal to 0, I varies from 1 to m, we name it as equation 4. Now, the slack variable s I squared is non-negative. Since s I squared is non-negative, from this equation 2 we have h I of x less than or equal to 0. So, since s I squared being a non-negative, we have from equation 2 h I of x less than or equal to 0, we name it as equation 5, and the Lagrangian multiplier constant lambda I greater than or equal to 0. So, from the given set of these three necessary conditions, we will get the condition for solving a nonlinear programming problem is f j minus lambda into dou h by dou x j equal to 0 and lambda into h I of x equal to 0 and h I of x less than or equal to 0 and lambda I greater than or equal to 0. So, from these three set of the necessary condition, we will get the Hundaker condition as f j minus summation I equal to 1 to m lambda I h power I j equal to 0, j varies from 1 to n, I varies from 1 to m. And the second condition lambda I h power I equal to 0, I varies from 1 to m, and h I less than or equal to 0, lambda I greater than or equal to 0. So, for the nonlinear programming problem of maximize z equal to f of x subject to the constraints h I of x less than or equal to 0, x greater than or equal to 0, the corresponding Hundaker condition is equation 1 and equation 2 and equation 3 and equation 4. By making use of the similar argument, we can obtain the Hundaker condition for a given nonlinear programming problem if the objective function is minimum subject to the constraint h I of x greater than or equal to 0. Now, with this help of this Hundaker condition, now we try to solve a problem. The problem is maximize z equal to 2 x 1 minus x 1 squared plus x 2 subject to the constraints 2 x 1 plus x 2 less than or equal to 6, 2 x 1 plus x 2 less than or equal to 4, x 1 x 2 greater than or equal to 0. So, the given nonlinear programming problem involving two decision variable, therefore, n value equal to 2 and two set of constraints, both are inequality constraints. So, m value equal to 2. So, the given nonlinear program involving two decision variable and two set of inequality constraints. Now, with the help of Hundaker condition, we try to obtain the optimum solution for the given nonlinear programming problem. For the given problem, our f is 2 x 1 minus x 1 squared plus x 2, and from the first constraints, that is 2 x 1 plus 3 x 2 less than or equal to 6, we will get our h 1 of x is 2 x 1 plus 3 x 2 minus 6, and from the second constraint, that is 2 x 1 plus x 2 less than or equal to 4, we will get the h 2 of x is 2 x 1 plus x 2 minus 4. So, for the given nonlinear problem, f of x is this one, h 1 of x is this one, and h 2 of x is this one. Now, the corresponding Hundaker condition is, the first condition is f j minus lambda h j equal to 0. This condition gives us the partial derivative of this function with respect to s, that we have 2 minus 2 x 1 equal to 2 into lambda 1. Now, for this partial derivative with respect to x 1 is 2. So, plus 2 lambda 2. So, the partial derivative of this function with respect to x 1 by making use of the equation f j f 1 minus lambda h 1 equal to 0 gives us 2 minus 2 x 1 equal to 2 lambda 1 plus 2 lambda 2. Then, you by making use of the same condition with respect to the variable x 2, this Hundaker condition gives us 2 equal to 3 lambda 1 plus lambda 2. So, the first Hundaker condition f j minus lambda h j equal to 0 gives us 2 minus 2 x 1 equal to 2 lambda 1 plus 2 lambda 2 and 2 equal to 3 lambda 1 plus lambda 2. We name it as equation 1 and 2. Now, the second Hundaker condition lambda h equal to 0 gives us lambda into h 1 of x, which is 2 x 1 plus 3 x 2 minus 6 equal to 0, and the second condition lambda 2 into h 2 of x, 2 x 1 plus x 2 minus 4 equal to 0. So, the second Hundaker condition lambda h equal to 0 implies the equation 3 and equation 4. Now, the third Hundaker condition is h less than or equal to 0, which gives us h 1 of x less than or equal to 0. Therefore, we have 2 x 1 plus 3 x 2 minus 6 less than or equal to 0, and h 2 of x less than or equal to 0. So, we have 2 x 1 plus x 2 minus 4 less than or equal to 0. So, the third Hundaker condition h less than or equal to 0 gives us the equation 5 and 6. Now, this is a nonlinear program involving two Lagrangian multiplier lambda 1 lambda 2. So, the fourth Hundaker condition is lambda 1 lambda 2 greater than or equal to 0. So, the Hundaker condition for the given nonlinear programming problem is this one. From this Hundaker condition, we got these 6 equations together with lambda 1 comma lambda 2 greater than or equal to 0. Now, by solving this 6 equation, we get the value of x 1 x 2, which optimize the objective function, which we will discuss in details. Let us have a break. Welcome back. Before break, we derived the Hundaker condition for solving a nonlinear programming problem involving more than 2 constraints. Now, with the help of this Hundaker conditions, we try to solve this problem. For the given problem, the Hundaker condition gives us this 6 equation. Now, by solving this 6 equation, we try to get the optimum solution for the given objective function. So, the Hundaker condition gives us this equation, we name it as equation 1 and 2, this is 3, 4, 5 and 6. Now, we consider the case of lambda 1 equal to 0 and lambda 2 is also 0. So, the first case is both lambda 1 and lambda 2 equal to 0. By taking lambda 1 equal to 0 and lambda 2 equal to 0, the equation 1 gives us 2 minus 2 x 1 equal to 0, and with this value of lambda 1 lambda 2, equation 2 gives us 1 equal to 0. So, for the case lambda 1 equal to 0, lambda 2 equal to 0, equation 1 and 2 implies these two equation. Now, if we consider this equation 1 equal to 0, which is highly impossible. So, for lambda 1 equal to 0, lambda 2 equal to 0, our equation 2 gives us this equation, which is not possible. Therefore, we cannot get the optimum solution for the case lambda 1 equal to 0 and lambda 2 equal to 0. Now, we consider the next case. Our case 2 is lambda 1 equal to 0 and lambda 2 not equal to 0. So, for the value of lambda 1 equal to 0 and lambda 2 not equal to 0, now equation 3 vanish, and for lambda 1 equal to 0 and lambda 2 not equal to 0, by making use of equation 4, since lambda 2 not equal to 0, we have the equation 2 x 1 plus x 2 minus 4 equal to 0. Now, by making use of lambda 1 equal to 0 and lambda 2 not equal to 0 in equation 1, equation 1 implies 2 minus 2 x 1 equal to, since lambda 1 equal to 0, this term becomes 0 and lambda 2 becomes 2 lambda 2. Now, for the values of lambda 1 equal to 0 and lambda 2 not equal to 0, the second equation gives us 1 equal to 3 into 0 3 and lambda 2. So, for the value of lambda 1 equal to 0 and lambda 2 not equal to 0, equation 1 and 2 gives this set of equation lambda 2 equal to 1 and 2 minus 2 x 1 equal to 2 lambda 2. Now, since lambda 2 equal to 1, this equation becomes 2 minus 2 x 1 equal to 2. From this, we can get the value of x 1. So, minus 2 x 1 equal to 2 minus 2, which is 0, which gives us x 1 equal to 0. Now, by making use of the value x 1 equal to 0 in this equation 2 x 1 plus x 2 minus 4 equal to 0, we have x 2 equal to 4 minus 2 x 1. So, 4 minus 2 into 0. So, 0, we have x 2 equal to 4. So, for the case lambda 1 equal to 0 and lambda 2 equal to 0, we got the value of x 1 equal to 0 and x 2 equal to 4. Now, with this value of x 1 equal to 0 and x 2 equal to 4, the equation 6 is not satisfied. With this value of x 1 equal to 0, x 2 equal to 4, the equation 5 does not satisfy, because x 1 0 this term vanished, x 2 equal to 4, 3 into 4 12, 12 minus 6 6, 6 less than 0, which is not possible. So, for the value of x 1 equal to 0, x 2 equal to 4, the equation 5 does not satisfy. Therefore, the case lambda 1 equal to 0 and lambda 2 equal not equal to 0 does not give the optimum solution to the given nonlinear programming problem. Therefore, we should omit the case lambda 1 equal to 0 and lambda 2 not equal to 0. Now, we consider the next case, wherein which lambda 1 non-zero and lambda 2 non-zero. So, we consider both the Lagrangian multipliers are non-zero, lambda 1 non-zero and lambda 2 non-zero. For the non-zero value of lambda 1 lambda 2, from this equation we name it as equation 3 and 4. We have 2x1 plus 3x2 equal to 6 and 2x1 plus x2 equal to 4. Since lambda 1 not equal to 0 and the whole equation 3 equal to 0, the only possibility is 2x1 plus 3x2 minus 6 equal to 0, which we write it as 2x1 plus 3x2 equal to 6. Since lambda 2 is non-zero, from equation 4 we have 2x1 plus x2 minus 4 equal to 0, which we write it as 2x1 plus x2 equal to 4. Now, by solving these two equations, I name it as equation A and this equation B. Now, by solving equation A and B, we will get the value of x1, x2. Now, by subtracting this, we will get 2x2 equal to 2, from this x2 equal to 1. Now, by substituting x2 equal to 1 in this equation, we have 2x1 equal to 4 minus 1, which is 3, which gives us x1 equal to 3 by 2, which is 1.5. So, for the case lambda 1 non-zero and lambda 2 non-zero, we will get the value of x2 equal to 1 and x1 equal to 1.5. So, x1 equal to 1.5 and x2 equal to 1. Now, by substituting this value of x1, x2 in equation 1 and 2, we have the following value: 2 lambda 1 plus 2 lambda 2 equal to 2 minus 2 into x1, which is 1.5, 2 minus 3, which is minus 1. So, we have equation C. Now, with this value of x1 1.5 and x2 equal to 1, in equation 2 we have 3 lambda 1 plus lambda 2 equal to 1, which is equation D. Now, by solving equation C and D, we will get the value of lambda as lambda 1 equal to 3.4 and lambda 2 equal to minus 5 by 4. Now, by solving this equation C and D, we will get the value of lambda 1 as 3 by 4 and lambda 2 as minus 5 by 4. Now, our Hundaker condition gives the value of lambda 1 and lambda 2 as both are greater than or equal to 0, but here lambda 2 value as minus 5 by 4, which is negative, which is not possible. Therefore, the case lambda 1 equal to non-zero and lambda 2 not equal to 0 never gives the optimum solution to the given nonlinear programming problem. Therefore, we should omit this case also. Now, the final case is lambda 1 non-zero and lambda 2 equal to 0. For the case lambda 1 non-zero, from equation 3 we have 2 x 1 plus 3 x 2 equal to 6. Now, by making use of lambda 1 not equal to 0 and lambda 2 equal to 0, from the first two equation we have, since lambda 2 equal to 0, from the first equation we have 3 lambda 1 equal to 1 and lambda 1 non-zero and lambda 2 equal to 0, this equation gives us 2 minus 2 x 1 equal to 2 lambda 1. Now, since lambda 2 equal to 0, the second equation gives us 3 lambda 1 equal to 1 and since lambda 1 non-zero and lambda 2 equal to 0, the first equation gives this equation. Now, from this lambda 1 equal to 1 by 3. Now, by substituting this lambda 1 value in this equation, we have 2 minus 2 x 1 equal to 2 by 3, which implies minus 2 x 1 equal to 2 by 3 minus 2, which is minus 4 by 3. From this, our x 1 value is minus 2 by 3. Now, by making use of this x 1 in this equation, we will get the value of x 2 also. So, from this our x 2 value is 14 by 9. By making use of this x 1 value in this equation, we will get the value of x 2 as 14 by 9. So, for the case lambda 1 non-zero and lambda 2 equal to 0, so we get the value of x 1 equal to 2 by 3. Now, by making use of the value x 1 equal to 2 by 3 in this equation 2 x 1 plus 3 x 2 equal to 6, we will get the value of x 2 equal to 4 by 9. So, for the case lambda 1 non-zero and lambda 2 equal to 0, our x 1 value is 2 by 3 and x 2 value equal to 14 by 9. Now, for this value of x 1 x 2, equation 5 and equation 6 are satisfied. So, the value x 1 equal to 2 by 3 and x 2 equal to 14 by 9 gives us the optimum value of the given objective function. So, for this value of x 1 x 2, our maximum z equal to 22 by 9. By substituting this value in the objective function, our maximum z equal to 22 by 9 and the stationary point x 0 is x 1 value 2 by 3 and x 2 value is 14 by 9. Let me recap. Given nonlinear programming problem involving n decision variable and m inequality constraints can be solved with the help of Hundaker conditions. For a given nonlinear programming problem involving n decision variable and m inequality constraint, the corresponding Lagrangian function is L of x s lambda equal to f of x minus summation I equal to 1 to m lambda I into h I of x plus s I squared, where lambda I equal to lambda 1, lambda 2 etc. lambda m are Lagrangian multipliers and s I which is s 1, s 2 etc. s m are called slack variables. So, this Lagrangian function gives us the necessary condition. With the help of this necessary condition, we can derive the Hundaker conditions. So, the corresponding Hundaker condition is f j minus summation I equal to 1 to m lambda I h I j equal to 0, j varies from 1 to n, I varies from 1 to m, and the second Hundaker condition is lambda I h I equal to 0, h power I less than or equal to 0, lambda I greater than or equal to 0. Solve the nonlinear programming problem of minimum z equal to 2 x 1 plus 3 x 2 minus x 1 square minus 2 x square subject to the constraints x 1 plus 3 x 2 less than or equal to 6, 5 x 1 plus 2 x 2 less than or equal to 10, x 1 x 2 greater than or equal to 0. So, with the help of the Hundaker condition, we obtain the solution for this problem. Thank you.